Good afternoon, student. Okay, we're still in week 2 lecture, chapter 1. We already talked about diffusion and drift current. And you have to know that, let's say we have a piece of silicon. So we have electrons. Those are electrons. And we have also holes. So electrons in holes. So this is most likely pure silicon. So we already explained the p-n junction is this the place where the holes in the electrons separate in the middle. So if we have, we already talked about doping. So let's say this is the thresholds. If we have the n-type is lower in number, than the p-type. So this is called an A. And also, so usually so an A means that the doping concentration on the, it's on the P side. If we have the P-type is lower, this is P-type, and the N-type is higher, we have the doping concentration is on the negative side. So N-type for silicon is mainly negative charge. P-type for silicon is mainly positive. So in this movement of electron, we have an electric field. How are we going to take into consideration? So E is equal to negative dvx divided by dx. So now we have calculation for the p-type. And also we have constant calculations for the n-type. Okay, for the p-type, the drift velocity which is represented as Vp, the velocity, the drift velocity on the positive type is equal to the mobility, the whole mobility, like how fast they're going on the positive, on the p-type, multiplied with E. So this one here, we call it aptly, is the whole mobility, and it's in centimeters cube per Vs. So as holes drift, what happened when they drift? They produce current. When we talk about drift, is the they go from, this is the PN junction, those are the negative and the positive. When they holes, most likely this one, when they drift, they come to this side. So usually they produce current. And this current is called I drift on the positive side. And most likely we take into account the amount of charge transferred per rate of time. So the amount of the transfer for charges in the p-type due to time. Where amount of charge transferred per dt due to time. Now we are accounting for the current, velocity, and now we need to know the distance. So holes distance travel. So usually dx, why? Because it's due to time, is equal to how fast they're going dt. It's physics. So for certain area traveled, a dx is equal to a vp dt. Why we include a? Because a is the cross-section area of the piece of silicon that we're using. So a is the cross-sectional area of the silicon, and that's in centimeters square. So now we can substitute formulas into the final drift current. And this is on the P side. So this is drift on the P side is equal to, this is IP. Let me put it into, so it's going to be IP drift. We already know that it's equal to dQp dt is equal to Q rho AVP, equivalent IP drift is equal to Q, rho is the concentration of the holes per centimeters cube, multiplied with the cross-sectional area, mobility for the positive, multiplied with electrical field. So most likely this is the current drift in the positive type or p-type. As for the n-type, velocity for the on the n-type is equal to same thing, rho, but on the n-type multiplied with E, and the drift current density, because we have also the drift, let me do it in the drift current density on the p-type. type. So the density is represented as JP drift is equal to the current for the drift divided by A, which is, we putting the formula, Q rho mu P, and then A and A gets canceled, and we left off with E. And this is going to be in A per centimeters squared. Okay, to continue here, the hole's diffusion current density will be represented as JP drift, or we are talking about the N type, which is the JN drift. We're talking about the drift one right now. We're not talking about diffusion. Drift current density is equal to Q on the N type, and then mobility of the electrons multiplied with electric field. And I think we had before, there's my 330 notes. It should be page number 8. So most likely this is for the drift current components. Page 9. Now we're going to talk about the diffusion current. So we're still on week 2. So diffusion current, same thing. We need to find the holes, diffusion, density. So we should know what's drift and what's diffusion. We already talked about it. And also we talked about what's doping. So JP drift, DRFF for diffusion, not drift, sorry, diffusion, is negative Q dP. This is the hole diffusivity, hole diffusivity on the positive side, multiplied dpx dt, and it's for the p type. For the N type, JN drift is equal to positive Q dN dNx dt, and both of these are in centimeters square per second. And this is for the N type. And dN is the electron diffusivity. Electron diffusivity. That's what a DN. Okay. PN junction. So most likely, this is page 8, page 9. Okay. PN junction. PN junction in equilibrium. In order to understand the PN junction in equilibrium, okay, let's say that we have before they are connected together, because when we have a semiconductor with hole p-type here, n-type here, the middle is the PN junction. Okay, before that, let's talk about these two pieces before they get connected with each other. So most likely this is the p-type, which is the doping, which is positive. That's the doping on the higher side. Doping on the higher side. Here is the n-type. Both of them are semiconductor made from silicon. So on this side, because it's all positives, and there's a lower concentration of negative, and here is all negative, and there's a small concentration of positive. So most likely we have Na to represent the doping concentration on the p-type. And here is Nd. This is the doping concentration on the n-type. N-type. Okay, so also on this side, we have the hole concentration on the p side, which is represented as P0, which is the hole concentration on the p side. So P0 is equal to number of the doping concentration on the p side, which is Na. Let's say we have the number of Na is 10 to the 18. Let's say here is Nd is equal to 10 to 16 per centimeters cube. So the number of doping concentration is the same thing as the hole concentration on the p side, but because this side, the majority is holes, there's a small drifting n-type, which is Nd. So most likely the Np0, which is the electron concentration of the n-type in the positive, is equal to Ni divided by Na That's also a formula. On this side, so we have the doping concentration on the n-type, which is Nd, is the same thing as the electron concentration on the n side, which is n and 0, n and 0. And it's going to be the same thing here, which is 10 to the power 16. Here it's going to be 10 to the power 18. Same thing for the little bit of positive. See these are a little bit of negative, and there's a little bit of positive here. P and 0 is equal to an I divided by the doping concentration on the n-type. Okay, let's talk about the energy level between these two types. So I'm just gonna, the energy level here is EC, and the lower side is EV. This is for the p-type. For the n-type, same thing. We have EC, we have EV, and in the middle is the IE. That's the reference. So most likely, if we have it on a graph, it should be looking like this is the x-axis. So this is the EI. So the number I'm going to put anything in red is going to be the positive number of holes, and anything in blue is going to be the number of the electrons on the other side. So on this side, the whole concentration on the positive side, which is pp0, is higher on this side. This is the pp0. And the np0 is really low on this side. This is the np0. On the other side here, on the n-type, the positive is really low. That's the p and 0, which is the number of positive on the n-type side. And the highly doped one with electrons is the n and 0, which is also called EFN. So this is most likely the one in green is the reference line. So most likely the line difference between here and here is called EG. EG is equal to EC minus EV. So usually that's the energy level between the p-type and the n-type. Let's talk about when we combine these two semiconductors, silicon semiconductors, together to form the p junction, and we talk about the p-n junction in equilibrium. One more thing before we go to the p-n junction in equilibrium. Just want to mention the thermal voltage. The thermal AGE thermal voltage is represented as VT. So VT is equal to number of doping on the n-type divided by mobility of the electrons is equal to the dp